Hey folks, it's Mr. Robeson here. We are looking at Taylor and Maclaurin series today, which is the end of sequence and series for us. So this will end this unit, which means we do have a test coming up shortly after this. But let's go through Taylor and Maclaurin series here first. So we've talked some about power series, and we know that we can write a function as a power series, right? By just finding a whole bunch of derivatives of these functions and then centering it at a certain value, say c, where any particular term has a coefficient of this guy right here, the derivative of the function at c over n factorial, and it also has a x minus c to the n. All right, that actually would be the Taylor series for a function. So if we can write this as an infinite function instead of just a polynomial that stops at some place, then that becomes a Taylor series. For the Maclaurin series, that c is just 0. So oftentimes we kind of use them interchangeably sometimes. But yeah, if we do have our center at 0, it is technically a Maclaurin series, or it's a special case of the Taylor series if you want. All right, but it's just what we've been doing so far for probably 2 or 3 sections now. All right, so let's find the Maclaurin series for f of x equals sine of x. So Maclaurin means that we are centered at 0. So that means we need to take a whole bunch of derivatives of this f of x, which is sine of x, and then we keep plugging in 0. So f of 0 is 0. F prime of x is cosine of x. F prime of 0 is 1. F double prime of x is derivative of cosine is negative sine of x. F double prime of 0, if you plug in 0 here, sine of 0 is 0. All right, so we have to keep doing this for a while because we're getting all these 0 terms, but it's not like they're difficult derivatives to take. So the third derivative is going to be negative cosine of x. So f triple prime of 0 gives us, well, we're going to get 1 from the cosine and the negative there, so it's negative 1. And have we recognized a pattern yet? Maybe we'll do one more or 2 more derivatives here. So derivative of negative cosine would be back to positive sine. So the fourth one at 0 is back to 0. But if you look, that's where we started. So it looks like we're just going to keep going through this path right here. And it's just going to keep doing this over and over and over again. So like this would be the 4th, this would be the 5th, this would be the 6th, this would be the 7th, this would be the 8th, this would be the 9th, this would be the 10th, this would be the 11th derivative, and so on. So it's just going to keep going through that sequence over and over and over again. All right, so let's see if we can write out the first few terms. So we'll have 0 times x to the 0 over 0 factorial. Not much happening there. Plus 1 times x to the first over 1 factorial. Oh, well, we finally got something there. Plus 0 times x to the second over 2 factorial plus negative 1 times x to the third over 3 factorial. Plus 0x to the fourth over 4 factorial plus 1x to the fifth over 5 factorial, right? We're back to 5, positive 1. So it looks to me like all the even guys have this 0 in front. So all those even guys are going to go away. And the next term here, the x to the 6th is going to go away. So the next term is going to be a negative 1 x to the 7th over 7 factorial. And can you figure out the pattern? The next term should be 1 x to the 9th over 9 factorial. And then it's going to be a negative 1 x to the 11th over 11 factorial. So if you notice, it's 1, 3, 5, 7, 9. And the exponents are also 1, 3, 5, 7, 9. It's all the odd guys. So we can say that sine of x is equal to the sum from 0 to infinity. Let's see, we've got an alternating sign. Let's just say to the n, because if we plug in 0, that gives us positive 1. If we plug in 1, that gives us negative 1, so that works for the sign. We've got x to the odd exponent. So the way we do odd numbers is 2n plus 1. Right? If we plug in 0 here, 2 times 0 is 0, plus 1, we get x to the first, which is what we want, x to the first for our first term. If we plug in 1, we get 2 times 1 is 2, plus 1 is 3, we get x to the third, which is what we want for our next term. All right, and then on the bottom is that same number factorial. So that would be 2n plus 1 factorial. So there is our Maclaurin series for sine of x. All right, now sine, of course, is probably one of the easier ones because it just goes back and forth between zeros and ones. Cosine would do the same thing. Other functions do get a little more complicated. right, so that's what we got. That was our answer on the last one. Where does it converge? All right, so what values can we plug in for x into this power series and get roughly or exactly the same value? Well, the way we find where a series converges is, well, we could do a ratio test. All right, so if we did a ratio test here, it'd be the limit as n goes to infinity of -1 to the n plus 1, x to the 2 n plus 1 plus 1 over 2 n plus 1 plus 1 factorial, absolute value, times this guy flipped over, right? We're dividing by the original guy. So we've got 2n plus 1 factorial over -1 to the n, x to the 2n plus 1. And we want this to be less than 1. All right, well, the absolute values are going to take care of the -1. If we distribute this 2, that's going to be 2n plus 2 plus 1. So that's 2n plus 3 factorial, which will be 2n plus 3, 2n plus 2, and then there's 2n plus 1, which matches the term up here, so we can stop writing out all the terms and just say factorial, and those will cancel. This, of course, will also be 2n plus 3, and the 2n plus 1, the x down here is going to cancel with that. And then we have 2 more x powers on the top, so it's going to leave us with just x squared. All right, so we'll have x squared, technically an absolute value, over 2n plus 3 times 2n plus 2 is less than 1 as n goes to infinity. Well, if we move these up over here, we get the absolute value of x squared, or just x squared is less than 2n plus 3 times 2n plus 2. And as we go to infinity, this also goes to infinity. So that means this is always going to be less than that. All right, so this converges. All right, our radius of convergence was infinity, from -infinity to infinity, meaning we can plug any value we want into here for x and just work out all the terms, and it will give us exactly the value of sine of x if we worked out all the terms. If we only worked out like the first, 5, 10 terms or something like that, it's going to be really close, right? And this is actually what your calculator uses to evaluate sine of x. Cool, huh? All right, so that's Taylor and Maclaurin series. That is, they're used for basically every sort of computation on your calculator and computers, so they're very useful applications in the world of math.